Let's finish up a little bit on aluminum welding. One thing that I don't think I mentioned last time was the need, because heat-treated aluminum alloys do not develop full strength. You can go with the non-heat-treated 5000 series aluminum alloys, and the maximum strength you're going to get is 35 to 40,000 psi yield strength. But you can weld those and you can essentially get 100% joint efficiency. And the Navy uses for catamarans and other lightweight ship structures 5000 series alloys because they have good corrosion resistance. They have the maximum strength around 35 to 40 ksi that you can get 100% joint strength. If you go to the heat-treated alloys, you can get 75 and 80 ksi strength. You can double the joint strength, but when you weld it, you're going to have 50% joint efficiency. You're going to be down at 40,000 because of the softening in the heat-affected zone. So you can weld the heat-treatable aluminum alloys, but you're always going to lose joint strength in the heat-treated alloys. The non-heat-treatable alloys, the 5000 series, you can get 100% joint efficiency, but you just don't get the strength weight advantage that you can with the heat-treated alloys. So as a result, in design of joints for aluminum welding, if I have an angle iron, or not angle iron in aluminum, but an angle coming into some other piece, instead of doing it like I do with a piece of steel, they actually, well, in a piece of steel, if you have some structure or some frame for a bridge or something, you would come in and you would just weld right in here. But in aluminum alloy, typically, you will take the base plate and you may put another plate on here that you can weld over a long area. And now when you bring in this other piece, you're going to weld it to this plate and you'll weld over a much larger area because the joint has half the strength. You're going to put gussets and other things in here in order to be able to get longer joints. These typically are going to be fillet welds. I mean, if I was making a joist out of steel, I just bring the two in here and I put a fillet weld on there. The steel strength, the weld strength of the steel weld for typical strength steels is equal to, or maybe even 30–40% greater in the weld than in the base material, because the faster cooling rate of the steel gives a finer structure and greater strength. In the heat-treated aluminum alloys, I'm not going to have that advantage of a stronger weld, and so I do all kinds of things like put gussets and stuff in the structure, which just adds to the cost of the structure. But it is the typical way they do it. A lot more clever, if you will, a lot more attention to the detail of design of the joint in aluminum structures than in steel structures. Steel structures, sticking them together, assume you're going to get 100% joint efficiency, leave it to the welding engineer. Aluminum structures, if it's heat-treated aluminum alloys, you assume you will not get 100% joint efficiency, and you're going to do something in your design to put your joints in a less highly stressed location or reduce the stress on the joint. So just to bring that up. Aluminum is weldable, very weldable, more weldable than steel by electron beam, less weldable than steel or other materials by laser, and in the other tapes when I talk about laser weld, I'll talk about the reason, but basically aluminum is a wonderful reflector of light, and laser is just light energy, and so I only get about 5 to 10% of my energy in on a laser weld in aluminum, whereas electron beam, the electrons penetrate the aluminum and you get nearly 100% energy absorption with electron beam. So if I want to use a high power density process, electron beam is the one of choice. We've talked about resistant spot welding briefly, where you take two sheets and you clamp them between two copper electrodes and you pass a big current for a tenth of a second, and I think I passed around a spot weld at one point, but that's the way you typically put automobile bodies together. In theory, you can spot weld aluminum sheet for automobiles. The thing is, Ford has a spec for steel sheet that you have to get 2,000 welds out of one of these copper electrodes. By the way, the resistant spot welding process was invented by Elihu Thomson in the 1880s. He was a professor of electrical engineering here at MIT, and he was second only to Edison, Thomas Edison, for the most patents issued to him. or to anybody at that time. And he and Edison started a little company up here in Lynn, Massachusetts. Anybody know the name of the company? It's now known as General Electric. And that's where, I mean, there's a lot of Navy aircraft engines made up there today. They used to have a marine division. They used to make marine turbines and marine gear and stuff like that. But that business is gone away to offshore mostly. But anyway, Elihu Thomson and Thomas Edison founded General Electric right up here in Lynn, Massachusetts. And the plant's still there, and it still looks about the same way it did in 1880. Even if you go inside, they haven't. Anyway, what else do I want to say? So anyway, in resistance spot welding, for steel, you get about 2,000 spots. That's a Ford spec. For the Nissan NSX or whatever, they actually got 80 welds before they had to change the copper tips. And the reason is, the aluminum is a wonderful conductor of heat, the copper is a wonderful conductor of heat. When you try to pass this current, you generate a lot of heat at the interface, and aluminum melts at a lower temperature, alloys with the copper, and you start destroying your tips very early on. If you try to make a high volume car, like a Ford Taurus, it would probably double the cost of the frame to make it out of aluminum. So people talk about, and Alcoa was pushing the all-aluminum automobile. Well, we built all-aluminum automobiles, Duesenbergs and stuff, in the 1930s. So it's not as if you need a new technology to do this. What you need is a infinite-sized pocketbook if you want to do this on large scale, because you would add 10 or 20% to the cost of a Ford Taurus. I mean, doubling cost of the structure, I mean, that doesn't include the seats and the engine. In fact, the most expensive part of an automobile is the engine. The second most expensive part, anybody know what it is? Nope, seats. The seats. The frame is like third or fourth most expensive component. Typical frame on a Ford Taurus is worth somewhere between $500 and $1,000. But if you make it out of aluminum, you're going to add $500 to $1,000 of extra cost just in the welding, because the welding, if you try to do spot welding. So if you're trying to sell a Ford Taurus for $18,000 and you start adding an extra $1,000 or $2,000 of cost, that's, you know, you're going to have a hard time competing against Toyota or whatever. However, if you're selling a $40,000 Audi, where people are not buying it based on cost, they're buying it based on performance, then what's the big deal? You're only making 50,000 of them and things like that. So it's not that we can't weld aluminum. It's that economically it doesn't make sense unless you have $4 a gallon gasoline. Now, it turns out most of the world does have $4 a gallon gasoline. But the thing is, everybody wants to export automobiles to the United States, so they don't make aluminum auto bodies, they make steel auto bodies. Even though it would make more sense in virtually all of Europe and most of the rest of the world to make aluminum automobile bodies, they're not economical in the United States, so they make everything out of steel.
What about like light aircraft, things like that, like Cessnas? Those are pretty much all, right?
Those are pretty much all aluminum, although a Lear is almost all composite now, right? Well, when you're paying $8 million, $10 million for an aircraft, you can. But you don't really worry about recycling those, because you go to they just keep taking those parts off old aircraft and putting them on new aircraft all the time, because the parts cost is so expensive because of all the insurance you're buying with each one, right?
They're not mostly welded, though, right?
No, they're riveted. In fact, I like to tell the story of a guy 20 years ago was getting a tour of a Boeing plant, and they were so proud of their welding of their aluminum sheet. Oh no, not the welding, it was adhesive bonding of their aluminum sheet. They had developed this adhesive bonding technology, and it was wonderful. And they wanted to show it to him, so they went through the plant and they showed him the adhesive bonding, but he noticed they were putting rivets through as well. He said, "Why are you doing that?" I said, "Oh, just to be sure." Okay? So there's the confidence they had in their adhesive bonds, which is a good thing. They don't have any better confidence, because the big problem with adhesive bonds is after, well, in the 1980s, when they were trying to reduce the weight of automobiles, they started adhesive bonding some of the steel door flanges and stuff, what they call the hem flange on the door. There's the outer panel and the inner panel of steel. They decided to adhesively bond them. And those adhesives lasted for almost a year. Okay, now and because those adhesives, and you should have gotten this lecture in the adhesive bonding stuff, the adhesives are basically water soluble, and guess what? It rains on a lot of automobiles. Okay, surprise, surprise. And they were trying to use cheap adhesives on the order of $1 or $2 a pound for the adhesives. Nowadays, they're using $10 a pound adhesives in automobiles, and the adhesives will typically last 5 years, maybe even 10 years, if it's not too wet around. But it's out of warranty by that time, so who cares? And it's just the door, so your door kind of rattles and creaks and things like that. In aircraft adhesive construction, where they really are relying on it, you may be paying $100 to $400 a pound for the adhesive. And it really gets down to very sophisticated polymer chemistry and moisture rejection. You have to go with polymers that just don't absorb moisture over long periods of time, and that gets a little pricey. So adhesive bonding works on sheet metal structures. It's just a question of you got to be careful. I mean, I saw a number of failures, some of which killed some people, in the 80s when they went in with these $1 and $2 adhesives. Okay, doors would just fall apart in a fairly mild crash. But they've gotten around that mostly, so it's okay to drive your car, probably. You got a better than even chance of making it home. So aluminum can be welded, but it's the same type of story I told you before. The material cost is only about 10% of the actual final fabricated cost. And it turns out, steel being cheapest, it also turns out steel is the cheapest to weld. Aluminum being 2 to 3 or 4 times as expensive as steel per pound, but on a volume basis being only about twice as expensive, cost about twice as much or 3 times or 4. You know, it's more difficult to weld aluminum and more expensive. But if I go to titanium, which costs 50 times what a piece of steel does in equivalent volume, or 25 times in equivalent volume, it'll cost 25 times as much to weld, just because of all kinds of other little problems with it, which was the next thing I was going to talk about, was titanium welding. Any other questions on aluminum? Titanium welding, I'm going to talk primarily about submersibles, since this part of the course is sort of designed for people in the Navy. You already know why you want titanium submersibles: high strength, lightweight, and it turns out if something sinks, well, you would like something that actually pops to the surface when you lose power, okay? And so you like strength to weight ratio is just as important in a submarine as it is in an aircraft. Maybe a little bit slightly different reasons. You want it to float to the top rather than the aircraft. You're looking for the aircraft to stay up there high. In this case, you'd like this thing to float to the top. It also has fantastic corrosion resistance. It's non-magnetic. Its only real problem is it costs $30 a pound. And if you're talking about, well, for a Seawolf class submarine, the whole mechanical and electrical was $500 million roughly. $2 billion for the sub, but only a quarter of that is HME, right? The rest of it's, you know, weapon systems and radar and sonar and all that other stuff. Just like an aircraft carrier, the hull's not that expensive, right? It's all those aircraft you have to put in it, right? We'd like to weld heavy section titanium, and the United States has spent several tens of millions of dollars trying to figure out how to weld 1, 2, 3, and 4-inch thick titanium. The Soviet Union, on the other hand, came out with the Alpha Sub in 1980, and they probably had spent just R&D the equivalent of $100 million, or maybe even a couple $100 million. So I mean, they outspent by order of magnitude or more. But we've already talked a little bit about the problems with the Alpha Sub. It's noisy. It had cracking, creep fatigue interaction, cracking problems. But it was a real blow to the Navy in 1980 when the Soviets supposedly leapfrogged them. It wasn't much of a leapfrog because the frog died on the other side, but nonetheless, it really was a big political problem in Congress. And I think I told the story about how in the mid-'80s, Congress, when the Navy was trying to sell the Seawolf, the SSN-21 program, Congress said, well, build it out of titanium, even though Congress didn't know anything about if you could build it out of titanium, except the Soviets had built one. All right, no, Congress said, we don't want you to build one out of titanium. I forgot. We want you to leapfrog the Soviets and build an all-composite submarine. Well, if you want to see what costs are, I mean, I showed you the space shuttle, the little piece of the X-33, at $10,000 a pound fabricated, right? So now we're going to go with the composite structure for a submarine is like 4 to 6 inches thick, okay, for the wall, because it's not as strong as the metal, right? So you're talking about, and something that's non-repairable. That's a wonderful thing, okay? I mean, you ever have a problem and you got to cut a hole in the submarine, well, you just scrap the submarine. It only costs you $100 billion for a single sub. So there's a reason why composite submarines have not gone very far. And in fact, I don't know, there may be some small submersibles that have been made out of composites, but I don't even know that I've heard of that. But certainly, the Navy has built titanium submersibles. The Seacliff, and I think the Alva now has a titanium hull. I think it had steel originally, but it's got titanium. The Seacliff was a spherical submersible that the Navy built in, I think, the early 80s, and it had something like a 1.6 or 1.8 inch thick wall, 7-foot diameter sphere, a little cramped, but you could go down real deep. And they tried to weld it with gas metal arc welding, where you have a titanium wire feeding in, and they were building it at Mare Island Naval Shipyard. And this is what David Taylor had been doing all this research on, was gas metal arc, because that's what we use, you know, in the shipyards to weld the steel subs. And they finally gave up. They could not get it to work in production of the Seacliff, which is sort of a prototype production. And they finally finished it with gas tungsten arc. Gas tungsten arc can put down good 2 pounds an hour of weld metal. Okay, very slow, very expensive, very high distortion, because you're putting down small weld beads. But that was the only way they could finish the Seacliff, was to switch to gas tungsten arc. So if we look at heavy section titanium welding, gas metal arc doesn't work. The Navy did a lot of research on it, and in the laboratory they could make nice small plates and get good welds, but if you ever try to make a 10-foot weld or something like that, there's all kinds of defects. It basically is an unstable arc. And we don't have to go into too much of that. Of course, the other thing we use with steel is submerged arc welding, where you have this granular flux you pour over the surface. And it turns out the very first contract I ever had back in 1977 was the submerged arc weld titanium from the Office of Naval Research. And this is one of those welds. And aside from poor bead shape, you can make really nice welds. You'd have to do something to improve the bead shape a little bit. But good quality. The only problem is the flux I had to make by buying single crystal calcium fluoride optics and crushing them up, okay, to get high enough quality chemistry to get a good weld deposit. Most calcium fluoride you have has 1% calcium oxide. The oxide, in the heat of the arc, the calcium oxide gets decomposed, the oxygen gets into the titanium, and oxygen is to titanium as carbon is to steel. It hardens it and turns it brittle. So you just couldn't tolerate the cheap flux that you could get for $10 or $20 a pound. Plus, it turns out, we did some economics on it, in steel you use about 1/2 pound of submerged arc flux for every pound of metal deposited, wire deposited. In titanium, it's more like 8 to 10 pounds of flux for every pound of weld deposited. So you would be talking about something like $500 a pound of titanium metal deposited for the cost of the flux. So it works, just not exactly economical. The Soviets didn't worry about economics. They had a completely different system. If the general said to do it or the admiral said to do it, you did it. And you didn't care what it cost, okay? So submerged arc, it works. This one just doesn't work technically. Okay? It might work in the lab. Big problem is price here, so that one doesn't work. But the Soviets built one, and we wanted to know how they built one, and so this is one time I did actually have a security clearance and used it, so I can't tell you how they built it. However, if I was a guessing man, and this I actually figured out before I had that security clearance and learned anything else. And I just got this by the literature. And I was actually at a workshop down at David Taylor when I listening to titanium welding that other people have been doing, when I figured out how the Soviets had to have done it. And they did electro slag welding. I passed this around a couple of times. This one was made at Oregon Graduate Center, but so far as I know, the first electro slag weld made in this country or outside the Soviet Union. Remember, electro slag is where you put two heavy plates. So you might have two heavy plates. You put them together like this. You put some copper shoes on the side that are water cooled. You feed a wire down in here, and you put a couple of pounds of flux, or you put a pound of flux down in here, and that flux gets used over and over. You basically are using the flux. You start with an arc on a base pad that you're going to throw away, and the arc starts the flux melting. Once the flux gets molten, it actually acts as a resistive heating element, and you're just passing hundreds of or even thousands of amps through the hot slag, and the heat is generated by resistive heating in the liquid flux. So who cares if I'm paying $100 a pound for my slag? Okay, I get to make a 10-foot weld with that one thing of slag. So the first electro slag weld in titanium was made right across from my office. The first one that anyone knows of in the United States, or that I know of, anyway. The French did a little work in the mid-'80s. That electro slag weld was done probably 1980 or 81. This was done in the mid-'80s at Oregon Graduate Center because basically the Navy classified the work on this after I showed that it could be done. Well, the Soviets had already showed it could be done. But then they kind of quit publishing on it. They were publishing on it in the 60s and the 70s. And then all of a sudden they sort of quit publishing on it. And so about 1980 at this workshop I thought, well, you know, they were publishing on this and they quit publishing on it. What happened? So that was one. Another thing that they were publishing on, that they quit publishing very much on, they were publishing on in the 60s and 70s. So electro slag is a process that could be used to weld titanium. And if you were a betting person, you could bet on that as a good process. Okay. And you can weld heavy sections very efficiently. But you can only do it in a vertical position. It's hard to turn these great big submarines around to do that. No, copper is water cooled, so it doesn't melt. If it does melt, you got a problem. But you're just melting the sides of the titanium. And in fact, the original problem we had is titanium and the flux have the wrong resistivity ratio compared to steel electro slag, which is what the Soviets had a huge experience with more than anybody else. And you can kind of see how the Soviets got into electro slag. They were, the Patton Institute still is the world's electro slag technology institute because Professor Patton claims to have invented the electro slag process. So they did a tremendous amount of work on that process. And they learned how to weld titanium by that process. The problem is that it's basically just a vertical casting with two copper, water-cooled copper sides and two titanium sides. The problem with the wrong flux electrical resistivity to wire resistivity is you end up depositing the metal so fast that it hardly melts the sides of the titanium. And the first one we ever did, we took the water-cooled copper molds off and we could take the titanium sides off too. And we just ended up with the titanium casting. But we did a weld that tall in about 10 minutes, okay, about an inch thick. It was pretty impressive. But it was also impressive that we really didn't get fusion, okay, to the sidewalls. But anyway, you can then develop things, and obviously you can see on this one, if you get the right type of flux and everything else, you can develop the process to get it. The other thing is you have to use AC current. It turns out the fluxes that you use will decompose with the DC current by just straight electrolysis. So there are a few little tricks, but the Soviets had worked those out. But that will only allow you to do vertical up welds, and you need something else. So another thing is what the Soviets called SemiSubmerged Arc Welding. And it has nothing to do with this type of submerged arc welding. And what happens is, if you're doing gas tungsten arc welding, which is a very slow process, you typically can't go above a couple of 100 amperes. So you have a tungsten electrode, W is the symbol for tungsten or Wolfram in German, and you weld this little bead here, and you're lucky if you get an 1/8 of an inch depth of penetration from that process. It turns out the Soviets learned that if I put a little layer, just paint on a layer about a 1/4 millimeter thick of certain types of fluxes like strontium fluoride. They tend to be halides, fluorides and some chlorides. I could get maybe a 1/2 inch deep penetration, and I could run this arc up to 1,000 amps, whereas this one might be limited to 150 amps. If I actually take that electrode and I might start it on the surface, but when I get going, this weld pool will be depressed. There's a force of the arc that depresses the surface, and I actually then now drive my electrode beneath the surface. So what's semi-submerged here is the tungsten electrode is buried beneath the flat surface of the plate. And now I'm putting all my heat in. If you will, maybe I'm only getting a 1/4 inch of penetration, but I'm doing it a 1/2 inch deep. I'm basically plowing through the zone. And so if I was someone who wanted to weld 2-inch thick titanium, I could prepare a joint like this, and I could put in a 1/2 inch deep weld here. I could put in a 1/2 inch deep down here, and then I could put in another 1/2 inch weld here. I have 4 1/2 inch, in 4 passes I could weld 2-inch thick plate with this semi-submerged arc process. Using the types of currents, 600 to 1,000 amps or more, that I might use with the old submerged arc process, but in a different process with just a very thin layer of this flux. This flux changes the arc energy. And this process, when the former Soviet Union, in the mid-'80s, when detente and glasnost and stuff, and the Soviet Union started looking for foreign exchange, they started selling this process in the West. And so you'll find the Edison Welding Institute has been working on this for 15 years under Navy sponsorship. And so they're working on it on stainless steel. A number of people have worked on it. We did some work in the early 80s on this, but we never got to that kind of sophistication because, frankly, 2-inch thick titanium is kind of pricey for university research. But anyway, these two processes are probably some of the more useful processes for welding heavy section titanium. It can be done. The Soviets learned how to do it, and if we had to do it, we could, but there are other problems with titanium submarines, such as the creep fatigue interaction, which I don't know that anyone's ever solved that problem. That's not a welding problem, but it is a problem with titanium alloys. So, now, so far as welding titanium in general, oh, there's one other process, and that's electron beam. The Navy in 1980 had a workshop. It was this workshop where I kind of brainstormed this idea of Electro Slag. Not that it was my idea, I just kind of was saying, what had the Soviets been publishing on that they had quit publishing on? And those are the two processes I just described. And then later, I actually did have a chance to see some foreign technology. But electron beam, at that conference, the first day was Navy Day, and the second day was Industry Day. And the conference was on welding heavy section titanium. On Navy Day, we all reported on 1, 2, and 4-inch thick titanium. I was the only non-Navy speaker. On Industry Day, we had Grumman and Boeing and all these big aerospace companies talking about heavy section titanium welding. The heaviest section any of them had ever welded was a 1/4 inch. Okay? So to them, heavy section was a whole different ballpark than what the Navy was interested in. It was sort of interesting to see the dichotomy. But since then, a few years ago, DARPA wanted to build not a spherical submersible, but a hot dog shaped submersible. What do you call them? I don't know. What do you, pardon me? Slender. Okay, a cylindrical object, right? And these are going to be 4 feet in diameter, and they were going to be 50 feet long. They're going to build 2 of them. This was all part of rapid prototyping. I don't know if you remember, after the Gulf War, one of the big things was rapid prototyping. You're going to put something in production and have a completely new part out there within 2 months that had never been designed or built before. And so there was this big program over here at the Draper Lab, which was non-classified. It was only the application of this 50-foot long submarine that was classified, and I never learned what the application was. But the contract and building it was completely non-classified, but they had to do ring-stiffened cylinders in 1/4-inch thick titanium. The wall of that submarine was 1/4-inch thick, with then stiffeners, T-stiffeners. And in fact, I ended up working with Draper on that. And most of what they did, since we're only talking 4 feet in diameter, you could go to electron beam vacuum furnaces in the aerospace industry and build up a bunch of these things that you would then finally put together by gas tungsten arc welding, which also works, but is very slow, okay? And that's how they built these. The first one was built in 6 months, okay, by just using aerospace technology, if you will. Problem is, you're limited to about 4 feet in diameter. Okay, so there's only so much you can do on those. But so the Navy has built titanium submersibles. Actually, that was by DARPA. But now, in doing that, when you're doing gas tungsten arc or electron beam or anything, welding titanium is a white glove process. A fingerprint on titanium has enough hydrocarbon in the oils in your fingerprint to create porosity in the titanium welds. Give you an example. Back in the late 80s, I was coming back. I'd just come back from a 2-week trip to Japan, and I get back, and there's a phone call from a company down in New Jersey that makes catalytic converters for the 747. Did you know there are catalytic converters on every jet? Because there's a lot of ozone up there in the air. I guess there's supposed to be less now than there used to be in certain parts. But anyway, and you can't breathe ozone, you get a headache. And so the air you breathe on a jet, commercial jet, has to go through a catalytic converter to get rid of the ozone. And they were, in fact, I had been reading in the paper on the plane home from Japan that Boeing was about to roll out the 747-400. Okay, so whatever year they rolled this out. And I get back to my office, and this company in New Jersey, in order to lightweight it, the 747-400 was going to be able to go all the way from Los Angeles or San Francisco to Sydney, Australia, which is over 12,000 miles, and you don't get any longer trips than that, because if it gets over 12,500, then you go the other way, right, around the sphere. So this was going to be the long-range 747, and they had to get the weight down to get the fuel up and everything. So ordinarily they'd been building stainless steel piping for the air in the passenger compartment, but they decided to go to titanium. And Boeing had a spec that they had these were gas tungsten arc welded, thin wall, like 1/8 of an inch thick, would have been stainless steel. Had an X-ray spec that you were not allowed a pore larger than 10,000ths of an inch in an 1/8 inch thick. Now, this is just the incoming air. I mean, if you actually had a leak in that, what's the big deal? But no, this was a Boeing spec, and you don't ever go try to change the spec. You guys should understand that, right? The spec is the spec, you know, and it will not be changed. You will do anything and pay any price other than try to change a ridiculous spec. I mean, the spec might have been absolutely adequate for something else that was highly stressed or critical, that not leak. But who cares if a little air leaks out into the cabin? Okay, you know. Anyway, air is not that hazardous a gas. Any case, they had this spec, and this company had been welding these things. They had been welding the stainless steel for years. They were trying to weld the titanium, and they had to make 4 welds in each one, and they had a 50% reject rate on the x-rays. And so if you had to make 4 welds with a 50% probability of finding a defect, you found they had never been able to produce a single module. And so the 747-400 was not going to roll out next month unless they fix this problem. So I had been gone for 2 weeks, and I called them up. I said, look, I don't have time to come see you. You just have to clean your titanium. You can't have fingerprints. You got to wear white gloves, you know, blah, 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 blah. It's not like welding a piece of steel and you can handle it with your hands, and if you get a little grease in there, it's no big deal. In titanium, it is a big deal. Even a fingerprint destroys you. So I told them how to clean it. And I get a call a week later saying, we still haven't passed. Our reject rate's still 75%, I guess, reject rate on their x-rays. And I said, look, I'll be down in New Jersey on something else tomorrow. If you can hang around till late afternoon, then I'll come by. So I came by about 5 or 6 o'clock that night after I'd done my other work in New Jersey. And I showed them, we walked through, and I walked through the whole process, and I showed them how to clean their titanium, which just means, you know, good alcohol degreasing, wearing white gloves, don't touch it with your hand, bag it before, you know, if you clean it today, put it in a plastic bag overnight. Don't leave it on the shelf just for the dust and the dirt in the air to rain down on there. You weld over a little bit of dust, and you can get porosity. I can tell you that same story up here at General Electric, aircraft engines, where they had porosity, and I told them how to do it. They were cleaning it with acetone, and I said, this is an electron beam weld. I said, is this reagent grade acetone? And the guy calls me back. He says, no, they get out of the 55-gallon drum in the back. Anybody in non-reagent grade acetone has usually got a film of oil on the surface. So anyway, I ended up going up to General Electric, and I took a slide. They had this little squirt bottle for the acetone. I took a little glass slide. There were 17 engineers from General Electric there, all looking over the shoulder and everything. And I took a little glass slide and I squirted some of the acetone when no one was looking on this clean glass slide. And you could just see, what do they call these, Newton's rings or whatever? When the acetone evaporated, it just left a little layer of grease. Okay? So they were cleaning it with grease, basically. And you're supposed to get the grease off. They were degreasing it with grease, basically. So anyway, in that story, which I haven't told you half of it, but I told the engineer that had called me in to go buy a bottle of reagent-grade acetone. And they started cleaning it with reagent-grade acetone. They had no failures for porosity in the welds in the next month. And he called up to complain that all he got was a letter of commendation. He got no cash compensation. What I didn't tell you in all this is because I was doing some research with him, he had asked me to do that visit for free. Okay, and I said, well, I didn't even get a letter of commendation, okay, for telling you how to do it, and I told you what to do on the phone without going up there. But anyway, cleanliness is next to godliness if you're welding titanium. It really is a white glove technique. So, you know, when the Navy said, well, we're gonna build a titanium structure at Electric Boat. Give me a break, okay? You're gonna have to build a whole new shipyard. It's an aerospace cleanliness. It's not an electric boat cleanliness, okay? To weld titanium. It's a whole different world and that's why the cost goes up so much. I mean, it's like dealing with medical equipment or something, okay? Your whole technology for doing the cleanliness goes way beyond anything you were used to before. Okay, any questions on titanium? Anybody have any questions on how to weld heavy section titanium? I don't think we're going to do it. I don't think we're going to try to join heavy section composites. I think we're going to have steel submarines for a while, and in fact, that's what the Navy's concluded. What's the next submarine? The next submarine material that they got out there, they've been pushing for the last 5-6 years. Anybody know? Steel, but stainless steel. AL6XN. This is an Allegheny Ludlam trademark, and the 6XN, the 6 stands for the fact that it has 6% molybdenum in it. So it's a stainless steel, and that 6% molybdenum means that this stainless steel is probably going to cost you about $3,000 to $4,000 a ton. Okay, but it's non-magnetic, and this stainless steel with that much molybdenum does not pit in seawater. Now, if you use 316 stainless steel, it would pit and stain in seawater, okay? So you don't want your submarine to corrode, and stainless steel does not do well in seawater if it's submersed, okay, all the time, and has potential crevices and things like that. So the Navy has been pushing for the last 5 or 6 years in the research area. The designers have said, aha, we can make a non-magnetic, cylindrical object out of this stainless steel, which is called a superaustenitic, okay? And it will be non-magnetic, and it will be relatively affordable, relatively being a relative term, okay? So that's what they're pushing now. They've given up on titanium. You can build, they built aluminum submersibles, which are even better, but again, you got tremendous distortion problems. And we don't even have these type of heavy section welding technologies for aluminum. When General Dynamics built the big aluminum spheres for the LNG tankers, they basically used gas metal arc welding, and they were welding 24-inch thick sections at the equators of these big spheres. And that was quite a technology to do that. So you can build big thick aluminum structures probably by gas metal arc or electron beam, but the costs get to be prohibitive there too. And you can talk about these wonderful aluminum strengths, but unless you can heat treat the whole submarine, solutionize it, temper it afterwards, you can only get 40 KSI in the non-heat treatable aluminum alloys. And so 40 KSI aluminum is not that exciting. When people think about an aluminum submarine, they're thinking of 75 to 80 KSI, except you can't weld that. No one has ever developed technology to get 100% joint efficiency at 70 to 80 KSI in aluminum. So what it is you got some designer says, oh, I got aluminum that'll go to 75 KSI, do the strength to weight ratio on that. And I say, aluminum with 75 KSI is a wonderful material, and then they go check with the welding engineer and says, can't do it. So that's why aluminum doesn't ever get off the drawing boards, okay? But you'll find it among the list of lightweight materials as for potential submersibles. Okay, any questions on any of that? Pardon me? Cast it. You could cast it. And you could put flanges on it and bolt it together with a big O-ring, right? No problem. Huh?
Then we have an answer to your question of what's the biggest single
Standalone object. That's right. Okay. Let's talk a little bit about welding. I mean, I'm kind of going down. We had steel, which is 95% of all metal, and then we have aluminum, which is 1.8% of the rest. I'm not going to talk a lot about welding of copper, but I will talk a little bit about nickel alloys, and titanium's in there. It's like 0.8%. The nickel alloys, and obviously there's lots of nickel alloys, Monel and whatnot, that are used in piping systems and stuff because of the corrosion resistance, although more and more is titanium. But remember, in the titanium, even though those piping systems for titanium, you're using gas tungsten arc, it's still a white glove technology, okay? You got to keep white gloves and keep things clean and bag them in plastic and things like that. The problem with nickel alloys is actually, there's not that big a problem in welding them, frankly. If you're just talking a Monel or something, they weld almost as easy as steel, except they're just wonderful crack systems. In fact, when we want to study solidification cracking in welding, we use Monel as the example, the prototype material. It just loves to put down a beautiful weld with a crack running behind it. And the reason is the same type of thing I told you about the aluminum alloys. The nickel alloys have a similar type of phase diagram where a highly alloyed nickel is going to be, this is percent of something else in the nickel, and this is temperature, and you've got this wide freezing range. It turns out to get the good properties in the nickel alloys, this is typically where we are out here. So you have a wide freezing range, and that's why you get the cracking. Same reason you get it in aluminum. In aluminum, we can either adjust to be very rich or very lean in the alloy composition. In the nickel alloys, well, you don't want to go very rich because you're trying to get high temperature out of a lot of these alloys, like for a turbine blade. So you can't go over here. You have to have enough to give it enough strength. If you're too lean, you can't get enough high temperature strength. So you actually end up in this region to get the high temperature strength. And you try to weld it, you have this big solidification range, big thermal stresses because of the big delta T, and you get cracks. That's not to say that we can't repair them. This actually is a turbine blade, and it does have a short corner, I just noticed. So don't cut yourself if I pass it around on that short corner. I'll grind that off. This is one where the crack was too big to be repaired. I mean, this crack, I think they typically only allow cracks up to about 1/8 or 1/4 of an inch on a used turbine blade to be repaired. But you can repair them by diffusion bonding. You can repair them by TIG welding. The problems for the high temperature alloys are that you typically have nickel-3 aluminum. Now you have aluminum in there and it forms this gamma prime phase, which has wonderful high temperature properties. The problem is it cracks big time. You really cannot weld a high aluminum nickel superalloy. And so what they do is they change that and use titanium, and there are actual plots you can go to for weldability, and you basically look at the aluminum titanium ratio. And the more aluminum that's replaced with titanium, the more weldable the alloy is. Direct correlation. Less cracking with titanium than aluminum. Not quite as good high temperature properties, but the weldable high temperature alloys like Inconel 718 have titanium replacing some of the aluminum. There are actually some alloys where they completely replace it. Can't remember which ones they are right now. But in general, it's just sort of a trade-off between the aluminum and the titanium and the weldability. They can be welded. A lot of research has gone into their weldability, mostly because you're talking very high value added parts. A turbine blade can be worth $4,000 and you screw it up and you can't repair it after you've tried to repair it improperly, then you've got problems. But you really can weld most of these things. This I've actually brought a couple of times. This is not really a welding thing on nickel alloys. This is actually a shroud from a jet engine, and so the turbines are going through here. Just to give you an idea, this actually has to do with brazing. If you haven't gotten to brazing yet, I'll talk about in the other lectures. Talk about brazing, but they put a honeycomb seal in here. And the honeycomb is just very thin nickel-based superalloy that's brazed up against here. And as the turbine blade ages, it's hot, it will actually grow in length because it creeps, right? It's under stress, centrifugal stress, and it's hot, and it will creep over time. And typically, I think they're allowed like 3% growth over the life of the blade. And so they actually have specs. You measure the length of the blade when it comes back, and if it's within a certain limit, you can repair it, and if not, you got to scrap it because it's already stretched too much. But in fact, you don't want to leave a gap there because you're trying to compress air here. And if you have a gap, things are going to leak past. So basically, they make this honeycomb structure, and the blade, as it grows, starts cutting into the honeycomb. And you can see here where the blades have cut a little path through the honeycomb. That makes the air seal from the spinning rotor to the stator case, so far as that goes. But that's just another thing with nickel-based joining. The last, well, let me just say a couple of things. Anybody here a diver? Got a diver? Okay. Well, let's talk a little bit about underwater welding. I may have to carry this over to after the break. Underwater welding. It's not something you don't want to weld underwater unless you have to, but sometimes for salvage, you obviously have to. The basic problem with underwater welding is both pressure and wetness, or cooling rate, or those are the two things. For underwater welding, you can either weld wet or dry. If you're welding wet, you can actually strike an arc underwater and lay down metal. The problem with it is, first of all, you're quenching the weld as you go. I mean, when you strike the arc, it will ionize gases. It will create. It will actually start to decompose the water into hydrogen and oxygen, and so you generate your own gas cavity right there. And the arc has enough energy in it that you can deposit metal. The problem is, as soon as you move along, the water comes in and quenches the hot steel behind. So if I'm welding steel underwater, I'm going to end up with a quenched structure, and I went to all these other troubles in steel to try to cool things slowly, and now I've gone to the exact opposite extreme. And so wet welding underwater tends to produce cracking and hydrogen cracking, because guess what? If you're wet welding, you're welding in a hydrogen atmosphere. The water is decomposed. So you're like a 50–60% hydrogen atmosphere. You got lots of hydrogen, you got a very hard microstructure that's been quenched, and you can get cracking. So no one welds structural permanent welds, or they some people do, but not a critical structural weld underwater. If they have to get a critical, they typically will build a dry habitat around it, pump the water out, put the welder inside the habitat, and he can weld. However, if you do that and you're down very deep, you run into other things, or even in wet welding, you run into other things. Typically, an arc is only stable below about 30 atmospheres. Now, anybody know what 30 atmospheres is in feet of depth? 300 meters, 1,000 feet. 1,000 feet. So the deepest you can go with arc welding, unless you want to go to a chamber that is basically a submarine that you can depressurize, okay? Now you got to build this around the structure. You also have to recognize that the cost of a tender up above is typically anywhere from $100,000 to $1 million a day, okay, for the ship that's going to be servicing the welders that are down there. If you're going down to 1,000 feet, if you're a diver, you know that to be able to prepare to go down and get in the water at 1,000 feet is like 2 days of preparation in a hyperbaric chamber to go down, and then to come back out is another 2 days, okay, of depressurization. So you're talking, if the guy gets 2 hours of working time down there, it may take 5 days on site to get 2 hours of working time. So underwater welding gets pricey real quick. I mean, you can get 2 hours of work for $5 million in some cases, okay? So there's been a lot of work on it. The oil industry does work on it. The Navy does work on it. It can be wet or dry. The problems are the pressure and the quenching from wet welding. But the pressure is a problem in any case. You really can't do anything below about 1,000 feet. And in practice, you don't do a lot below 200 feet. Now, so most salvage operations don't weld unless they absolutely have to, okay? You do a lot of fastening and bolting and things. That's enough for right now, and we can talk at the break if you want me to go through any more on the stuff. I could go through some chemistry.